So hi, welcome back to the second part. So we're talking about generating functions, and you already seen the root polynomial, which was an example of that. And so here's the general concept. So we have a sequence of numbers, a0, a1, a2, and so forth. And so it could be infinite, it could be finite. So if it's finite, you just add zeros. And to such a sequence, we can associate the generating function, which is the infinite series ai times, where the summands are ai times x to the I. And so there are some important remarks to make here. So if you see something like this, you might think about calculus, about convergence criteria, especially if you see the word function. Does it really make sense to put it in a number? This is just a notation, so it's just a name. It's also called generating series. And so for us, the generating function is really a completely formal object. It's a symbolic, algebraic way of putting all of these numbers just together into one object. The advantages are that you can manipulate this one object. You can for instance, you can multiply generating functions. We will see we can even take derivatives. We can do lots of interesting things with it, and this will help us to deal with these numbers, just all of these numbers at once. And so especially like the x here, the x is also just a symbol. Okay, so in most cases, that's the way you should just think about it. So if you've never seen this, let's just look at some examples. So let's just take 1 a bunch of times. So 1, 1, 1, 1, 1, 1, and then just zeros. Okay, let's take it n times. If this is our sequence, what is the generating function? Okay, so well, so it's 1 times x to the 0, which is just 1, plus 1 times x to the 1, which is x, plus 1 times x to the square, which is x squared, and so forth, until x to the n. And you're right, probably notice this should be n plus 1 times. Because you start counting from 0. So this is a typical mistake. We have n plus 1 times. So in this case, a0, a1, a2, up to an. And so this here in this case, these are all 1s. So they just get a polynomial, of course, because everything from a certain point on, everything will be just 0. Now, what mathematicians don't like about if you write it like this, so of course it's nice, you understand what's going on, but we have these dots there. Can we get rid of them? There's a trick how to do this. Very nice trick. Multiply by 1 minus x. Okay, so let's multiply it out. We get 1 times 1, which is 1. We get 1 times minus x, which is minus x. We get 1 plus x. This is plus x. We get, okay, so now careful, we get minus x squared, but also plus x squared. And now we get the idea what's going on. What you see is that these always cancel. And so if you go on like this, at the very end, what you will get is minus x to the n plus 1. And everything in between will cancel out. This is called the telescope sum. And so the answer here on the right side is just 1 minus x to the n plus 1. And so why does it help us? Well, let's just bring this on the other side. Let's just divide by it. If you do so, we get this formula. And You see on the right side there are no dots anymore. It's written very elegantly as a quotient of two polynomials. And this is a very nice, compact description with no dots anymore. And it's also easier to actually multiply these things and to take powers. So this is the way how you would usually write generating functions. Okay, let's make it more complicated a little bit. At least it looks like. Now we're going to infinitely many ones. So just one, and so forth. Okay, in this case you get 1 plus x squared, and so forth. Again, the question is, can you write this in a nicer way? Well, let's just use the same trick. Multiply by 1 minus x. Get 1. And now the same story unfolds. In between, everything cancels. But what does in between mean? Does it have an end? No, it doesn't have an end. It never ends. So it will just cancel out forever, which means that the right side is simply 1. And again, all of this is really, just formal. These are formal arguments. And so we can deduce that equal to 1 over 1 minus x. And so all of these formulas I'm writing here is something you should know by heart. Okay, this is important that you know this. So this rational function, so that's also how you would call this, 1 over 1 minus x is very important. It's also called the summation operator. So there's a section 9.5 in the book about this, where you learn why it's called that way, and it's very nice to deduce some interesting combinatorial formulas. I won't talk about this in the video. But please have a look at section 9.5 too. So I just wrote what we just seen again here. And so let's do a little trick here. Let's take derivatives on both sides. So what's happening? So on the left side, you just do this for every summand. This goes to 0, x goes to 1. X squared goes to 2x. Here's an x to the cubed. X to the cubed goes to 3x squared, and so forth. Now what happens on the right side? Well, you all can do this. You have to use the chain rule here. And so we will get 1 over 1 minus x squared. So this is, on the left side, this is the generating function for also a very interesting sequence. Namely 1, 2, 3, 4, 5, and so forth. Okay, so this pretty natural sequence has this generating function on the right. And now we can go on with this trick. So you take the derivative on and on and on times. So if you want to have something on the right side, will on the bottom of order n. The top part will also be just a 1. So if you do this, in this case, n minus 1 times, just taking the derivative, and you can check this out on your own. Just do a little bit more examples. And you will see that on the left side, what's going to happen is that you will have n minus 1 factorial plus n factorial divided by 1 factorial times x plus n plus 1 factorial divided by 2 factorial times x to the square, and so forth. Okay, so in this case, n would be 2. So we'd have 1 factorial plus 2 factorial plus 3 factorial divided by 2 factorial, which is 3. Okay, so this is the general scheme, what you will notice if you do that. And so, I made a mistake. So do you see where I made the mistake? Well, here on the right side. Because if you do that again, the 2 will come down. So actually, this is not correct. And hope you got really nervous because of this. We have an n-1 factorial on the right side. Now it's correct. Okay, again, these try to do this on your own to see why this is the correct formula. And now it still looks a little complicated, so let's simplify it. We divide by n-1 factorial here. So if we do that, divide by n-1 factorial, we get 1 over 1 minus x to the n on the right side. Left side we get 1 plus n times x plus divide by n-1 factorial. So it's n plus 1 factorial divided by 2 factorial divided by n-1 factorial. So this looks like a binomial coefficient. So this is actually n plus 1 over 2. And if you do the next step, well, what do we get? You would get something like this, n plus 2 over 3 times x to the cubed, and so forth. Okay, and so we see that this is what this looks like. That's 1 times x, and this is n over 0. Okay, so, well, what does this tell us? Let's write this differently. I claim what we get from this is the following formula. Get this. Okay, so let's check this out. R equals 0, you get n minus 1 over r over 0, and of course this should be in here. If r is 1, you get n over 1, then you get n plus 1 over 2, n plus 2 over 3, and so forth. So, and this was maybe a little bit fast, maybe a little sketchy, but this can be made completely precise, every step I wrote here, and you get this formula. Now, why is this a nice formula, and this will a very useful one? Because these coefficients you see here, we already seen them before. Remember the small table of counting? That's where these binomial coefficients were in there. Now, if you look at this also, there's something else should come to your mind. The keyword already mentioned, namely binomial coefficients. Remember the binomial theorem? Let's write it down. Let's just write it down for one very special situation. Namely like this. So we look at 1 plus x to the n, and so what we will get here is the sum from r equals 0 to n in over r times x to the r, and then here would be 1 to the n minus r. So I just leave it out. And so we see that this looks very, very similar. So somehow all we do is this is like a positive formula where on the right side you have a positive number, where here you have 1 minus x to the minus n, because it's in the quotient. And here we just have these binomial coefficients, and you might say, well, but here we only go up to until n. Well, you can just replace this by infinity if you like, because n over something which is larger than n just gives you 0. And so there is a certain nice symmetry here, and this can be made precise. So you should really compare this. These two formulas, and so they are related. So these two formulas are related by another nice combinatorial identity, which I just write down. And there's a box in the book which explains this. And so please look at table 9.2, which all kinds of these kind of identities like these. So it's very important that you get an idea about how to modify something, like how to work with these infinite series, and I hope kind of that it doesn't look so strange anymore. Okay, so we learned about all this black magic of generating functions. So what does this have to do with combinatorics? And so let's look at this here. So this is what you already know. So k plus r minus 1 over r counts the number of ways to put r identical balls in k distinct boxes. Okay, so this is something we know already, and of course now we can define br as l plus r minus 1 over r, the number of ways to put r identical balls, but now in l distinct boxes. And so the generating function, a0, which is 1 plus a1x plus a2x squared, and so forth, this is something we also know. That's just what we are talking about. This is 1 over 1 minus x to the k. And the same 1 over 1 minus x to the l is 1 plus b1x plus b2x squared, and so forth. So this is all okay. Now let's just for fun, let's look at what happens if we multiply these two together. So if we multiply these two together, what do we get? Well, we get 1 over uh, 1 minus x to the k plus l, of course. Let's also do this on the right side. So we have 1 plus a1x times 1, 1 times b1 times x. So it's a1 plus b1 times x plus a2 plus a1 b1 plus b2 x squared, and so forth. So let's just for a second think about what we're doing here. This is the generating function for the following problem: the number of ways to put r identical balls in k plus l distinct boxes. So that means if you, for instance, look at this coefficient here, let's just verify this. So in this case r is equal to 2, so that means we have 2 balls. And now we want to put them in k plus l boxes. Now what does this have to do with these two kind of smaller, seemingly smaller problems? Well, think about that we have k boxes here. Remember, these are all distinct, all numbered, and then maybe the other l boxes. And so what choice can we do if we have like 2 balls? Well, we can either put both of them in the first k many boxes. How many ways are there to do so? Well, a2. Or we could say, well, we put all of these 2 balls in the second class of boxes, in the l many boxes. How many ways are there to do so? Well, this is b2. And then we have a third option. This is really like the rule of sum. Namely, we put 1 ball in the first one and 1 ball in the second class of boxes. So the first one in the k many boxes, the second one in the l many boxes. Well, how many ways are there to do so in the first place? Well, a1, and we have b1 many choices for the second, to put them in the l many boxes. So we have a1 times b1 many choices. And so overall, this gives us precisely the answer we want. Now, I like this way of thinking about it because it kind of can come up with the same formula we've already seen again. So let's look at the generating function. Of the number of ways to put r identical balls in, let's just call it now n, so that it looks more like you've seen it before, distinct boxes. You already know the answer. This should be 1 over 1 minus x to the n. So, but now by using this way of thinking about it, we can just recover that. Why? Because you can think of n as being 1 plus 1 plus so often until plus 1. Which means now, if you think about it, so previously we had like these so and so many k plus l many boxes. And now we separate it into k many boxes and l many boxes. And then you see we can just take the generating function for this problem times the generating function of the other problem. Now we can just chop it in smaller pieces. If we do so, we can finally have only one box. And so what do we get? Well, we only have to figure out what's the generating function of the number of ways to put r identical balls in one box. Well, that's not so hard. There's only essentially always just one way to do it. So this means that the generating function for the number of ways to put r identical balls in one box is 1 plus, so there's only one way to not put it in there, there's only one way to put it, so there's only one way to put no ball in there, there's only one way to put one ball in there, there's only one way to put two balls in there, and so forth. This is the generating function for that problem. And I would just multiply it. For each, we do that for each box, we get the same answer, we just multiply it, so we take it to the power of n. And now this is 1 over 1 minus x to the n. So that's another way how we can see this. And I think it kind of enlightens how we think about it combinatorially. Okay, so here is kind of a summarizing example. Namely the following. So we wanted to compute the number of integer solutions of the following equation. x1 plus x2 plus x3 plus x4 plus x5 equal to r. Now we have some conditions, which makes the problem more interesting. Namely, x1 is squared equal to 3, x2 should be between 2 and 4, x3 is at most 2, x4 is even, and x5 is odd. Okay, and I'm thinking about whether, yeah, I think really I want not only integer, but I want all of them to be also non-negative. Okay, so integer. Okay, so no negative numbers here. Okay, so how do we do this? Well, we use the approach we just seen. Namely, in this case, in this situation, we see from a previous argument we had before that you can really think about the sub-problems, namely about each of, in this case, about each of these, how many ways there are to put them in each of these boxes, and then you multiply the generating function. So, the generating function equals, okay, let's look at the problem of putting these r identical balls into that first box. So this is now just a problem with x1. So x1 should be at least so as large as 3. So this should start from x to 3, x to 4, and so forth. Now here we multiply. There's a problem here. So in this case, the only range we're having is, in this case, that we can put in 2 balls up to 4 balls. So it's x to the 4. There's only one way how to do that. Now here, x3 should be at most 2, but it's not negative. So we start from 0. So 1 times x to the 0 times plus 1 times x to the 1, x to the 2. Okay, x4 should be even, no more restrictions. So it should be even, okay, so that means it starts from x to the 0. So 1 plus x to the 2 plus x to the 4 x to the 6 and so forth. And finally x5 should be odd. So there should be at least 1 in there. So x to the 1 plus x to the 3, x to the 5, and so forth. And now you see how easy it is to write this down, and that product will be the generating function. So in order to solve the problem for CR, we just have to figure out that coefficient we're interested in. And also, in many cases, it's much better to try to get rid of these dots here. And also, if you want to, whenever you have problems where you have actually, so in this case it doesn't look like this, but there are other problems, like, you know, if you modify this, but you have lots of powers here, it's always good to write it as a quotient of polynomials. And so that means in this case it simplifies. We can take out x to the 3. In this case you get 1 plus x to the square. Now we recognize this, so we can actually replace this here by 1 minus x, so 1 divided by 1 minus x. Okay, now let's look at this one here. In this case, you can either leave it, but of course, it's always good to take out a power, so x to the 2, 1 plus x squared. And if you like, you can also write this, as you've seen, as 1 minus cubed divided by 1 minus x. So if you like so, and sometimes it's useful, sometimes maybe not. And now we're here. Same thing, we have the very same and finally we're here. Now in this case, what did you do here? Well, think substitution. We have, in this case, this is x squared, this is x squared to the square, this is x squared to the cubed. And so we see what we have here is simply 1 plus variable squared plus variable to the cubed, and so forth. So this is just 1 over 1 minus x, but not x squared. And finally, here, well, what do? You take out the x. Once you take out the x, you have 1 plus x squared plus x fourth. We already computed that. That was 1 minus x squared. And so if you like, you can now completely summarize this, and you get a shorter answer to this. So let me try if I can do this, and I hope I don't make any mistakes here. So we have 1 minus x 1, 2, 3 times. And we have 1 minus x squared. Well, we can also, of course, here try to simplify this if you like. Let's just keep it here like this. Squared. And at the top we have x cubed, x squared, so x to the 5 times. Oh, wait a second, I forgot about the x there. You see, you have to be careful, so we have x to the 6. And finally we have 1 minus x to the cubed. And well, also here you see, maybe you can simplify further. I leave that to you. Maybe you can cancel out stuff. Never really know, maybe not. Well, as I said, I leave that to you. And so homework is, to play around with this. For instance, try to find C9. Try to find the 9th coefficient in the series, so we have to expand the right side. And also, please have a look following examples in the book. Well, essentially there are many of them, but all of them I couldn't single out don't do these or do them. Really try to look at most of them up to, so in these sections, up to example 9.14. Okay, so see you next week.